Okay. Um, Hello, guys. I guess we can get started. So for today's webinar, we'll be talking about AC versus DC coupled BESS, the differences between these two, the different inputs that you can insert in pvDesign, so that in the end, you guys will be able to know which one is going to be best for your project. So my name is Altair Veiga. I'm a principal consultant. I'm passionate for renewables and a sustainable world. I'm part of the customer success team at RatedPower, which is also part of Inverus, which is a US-based company. Right. So these are the sections that we're going to go over today. So we're going to talk about what's best, the types. We're going to do a case study, comparison summary, and in the end, we're gonna do a Q&A. So feel free to drop any questions in the comment section. And let's get started with what's BESS types. So BESS, also known as battery energy storage system, is a technology that can be used either as a standalone system or as an add-on to the conventional solar or wind renewables, as well as other sources of power. So I kind of skip like what a battery is because we already know what a battery is. We use it in our daily activities. In this specific case, we have the battery system that we can use with our PV in a hybrid mode. Or here on the other image, we can see the batteries being used with wind turbines. But also, again, you can use it with other sources of power, including a standalone system. So now we're going to talk about the types of BESS coupling. So we have AC coupled BESS, and we also have DC coupled BESS. So the AC coupling is the type of BESS that is located usually outside of the PV plant, and it can be charged and discharged by an inverter. So if we take a look here on the right side, we can see that the power being generated by our modules goes to an inverter, which from there either can go to the grid, to any other load, or it can also be used to charge our AC coupled battery, right? So this system is going to have its own inverter, which can also be charged either from the grid or from the power coming from the PV side. The DC coupling, so this is the type of BESS that is located within the PV plant area and usually near the power station. So again, the same principle, the power being generated from the panels. And then let's say that our inverter is, or our panels are producing way more power than what the inverter can convert. So that excess of power is going to be used to charge our batteries through a DC-DC converter, which it has different functions, but one of its functions is to adjust the voltage and to ensure the charging for our DC coupled BESS system here. So we're going to do a poll question. And the question is going to be, is the image below a DC or AC coupled BESS? So feel free to take a look here at the image, and then you'll be able to vote in the next few seconds. Okay, I guess we can start the poll. Okay. So it's still volts up here. Alrighty, so we actually got a pretty close results here, but the majority of the people said that this is a AC coupled BESS, and the answer is right. The reason of that is because this system is located again outside of the PV plant. So it is outside, and then from here we can see both containers. We have the battery container, and we also have the power conversion system container, which is where the inverter and the transformer is going to be to charge and discharge these batteries up here. So let's jump into the case study. So in here, we're going to talk about the differences in the layout, the differences in the bill of quantities, and as well as in the energy side. So in this case study, we're going to be using these inputs for the DC coupled BESS, AC coupled BESS. So here we're going to be using 18.48 megawatt AC power for both cases. The DC or the solar quantity on the DC coupled BESS here is going to be 23.85. On the AC couple is going to be 22. So we are actually increasing slightly here the DC-AC ratio to 1.29, whereas here we have 1.2. The reason of that is because the DC couple BESS is a charge, or those batteries are charged based on the excess power that our plant is producing. So any excess power that our inverter cannot use, we're gonna use that excess to charge our DC coupled BESS. So that's why I slightly increase the DC-AC ratio so that we can charge our BESS. But on the other side, we are enabling a curtailment of 16 megawatt hour for the AC coupled BESS, because the AC coupled BESS, we can charge it. So let's say that our grid has a limitation of exactly 16 megawatts, right? So we cannot inject more to the grid, anything above that. So if our plant is producing more than 16 megawatts, then that excess then is what we're going to be using to charge our AC coupled BESS. So, and then here on the battery, since we're doing this case study with similar components here, so the battery is also going to be similar, 8 megawatt AC, same thing up here, the capacity 8 megawatt hour, and with a supply duration of 1 hour. So, time to jump into pvDesign. Let's go over up here. So I'm going to clone this existing design, just clone it. And for the people that maybe it's their first time here, just a small introduction about pvDesign. But basically, pvDesign is a cloud-based software that allows users to quickly develop utility-scale solar projects. So let's start by inserting the inputs for our DC couple study first. So I'm gonna go up here, specific capacity. We need to use a 23.85. Our DC-AC ratio, we're gonna put 1.29, and we are getting about, let's see, sorry, here actually supposed to be 18.48. Alrighty. So now we're going to go to the battery section. We're going to enable this here. BESS type, we're going to be using a DC coupled BESS. Then power conversion system. So here we're going to be choosing the PMAX for our DC-DC converter. In this particular case, we're using 1,000 kilowatt up here. You're going to be using only one converter per inverter. For the battery container, we're going to be using a 500 kilowatt hour battery. And we want to use batteries in 4 of the power stations, right? So let me just have these here, 4 with a supply cycle of 1. So once we have completed, we can go ahead, proceed, and then run the design. But there's also other things that you guys can change here, the battery dimensions, the distances. Let's just go ahead and then click here to run the design. Okay, so if I zoom in a little bit, we can see here the power station. So this power station is where we have the central inverter and the transformer too. And alongside we have the 4 batteries for our DC coupled BESS. And because we have chosen to have 4 power stations with BESS, so we have 1, 2, 3, and 4, then this is what the layout can look like, right? So what we can do right now is actually download some of the documents, including the bill of quantities, as well as the energy yield results. Let's download this really quick here. So let's start off with the bill of quantities. And enabled. Now let's jump into the BESS system. So this is what we're going to have for the bill of quantities for our batteries. So we have here about 16 battery containers, each 500 kilowatt hour. We have about 8 DC-DC converters. So we're using 1 DC-DC converter per 2 batteries, and then 16 foundations and 16 terminal units. Now let's jump in and open the energy results, Excel. Enabled. Let's go to battery and let's scroll a little bit down here. Let's find 5. Okay. So add up here. So this tab that we are seeing right now is the battery energy tab in this energy Excel file. And we can see here the information energy losses data. So basically in here is where we're going to see the losses, right, that our system is going to have, which can then be used to charge our batteries. So in this particular case, we are using DC coupled battery. And we, if you remember, we increased the DC-AC ratio so that we could increase the amount of power that we're going to be using to charge our batteries. So we can see here, so the overpower loss, the power that our inverter cannot convert. And then we can see here on this other column, the overpower loss inverters with storage. So basically, since we have batteries in all of the power stations, so all of the losses that our system is having, we're going to be able to take advantage and charge our DC coupled battery. So right now, let's make a quick change and input the settings for the AC coupled BESS. So if we go here to the BESS, we scroll all the way up, and then we should choose this option. And the reason why this one is not showing is because for the AC coupled BESS, we need to have a polygon. We need to have a specific area to have our AC coupled BESS. So what we can do here, because we already have a site with this allocated battery polygon, I'm just gonna choose this option up here. And if you look up here, this is going to be the area that we are allocating for our AC couple. Now, you're gonna go to layout, power, again, to make some adjustments. So we're gonna decrease the DC-AC ratio, 1.2. And we're also going to enable a curtailment at the delivery point or the point of interconnection of 16 megawatts. Now we're gonna jump into the BESS tab. If we type in here, it should already be selected. So after that, we need to choose, so we can choose the inverter that we want to discharge our AC coupled battery. We can already leave this one up here. We only want one inverter per PCS. PCS is the power conversion system where the inverter and the transformer is going to be. A battery, going to be using the same capacity, 500 kilowatt hour. And then how many of those do we actually want? So we want to use 4 of the PCS containers with a supply cycle of 1 hour. And again, you guys can change things here, including the distances between the different blocks and including rotating your battery system here. So let's go ahead and then click run the design. Okay, so right now we can see here that we have 4 PCS where the inverter is, and per inverter over PCS, we have 4 of these battery containers. So what we can do now is download also some of the same documents that we did for the DC coupled BESS so that we can make some comparison. Let's do this too. So let's start with the bill of quantities first. Enabled system. So this is what the bill of quantity will look like for the AC coupled system. We can see that we have far more things compared with the DC coupled, right? So we have the inverter, we have more sections for the civil works like clearing topsoil, earthwork, trenches. So this is something that you can also use to make that judgment of which one of these best options do you actually want to use. Now let's open the energy Excel file. Enable battery. Let's go to the same tab or same row. Okay. All right. So right now we can see that we're going to be seeing the power or those losses on the clipping loss section, right? So here is where the grid can no longer take more power, and then that excess is then what we're using to charge our AC coupled BESS. So if you actually go to the first year hourly data, and we try to go to, again, the same row, so 7, 6, 5. So if you take a look here on this side, so at these particular hours, our grid is already reaching that full capacity that it can receive of the 16 megawatt hour. So that's why we can take advantage of that. If your grid has any cap, you can use that excess to charge the AC coupled BESS. So we have launched a new feature quite recently, which is the option to use sub-hourly data. So if you click up here, Meteor file, and then we click upload Meteor. So not only you can do monthly, hourly, but right now you can also use some hourly data, either 15 minutes intervals, 5 minutes intervals, as well as a 1 minute, which this is something that can be very important whenever you're doing this BESS analysis for your system. So in this case, we actually have one 15-minute interval. So let's actually choose this one, and then let's do run the design. Just quickly so that we can see the different outputs that we can get when we're using this sub-hourly data. Still loading. So now let's click here and then go to the energy yield results. Still loading, 1 second. Okay, so let's enable editing. Sorry, it's gonna be this one. Okay, so now if we go to, let's say, 3, 7, 8. Just gonna be doing like a similar comparison, but right now with the sub-hourly data. So if we take a look here, for instance, we have the times at, let's say, 11:07, 11:22, 11:37, 11:52, and we can see here the different power at different times that would be clipped, right? So that we can use to charge our batteries. And if we quickly go check the first here tab. So we can see here that right now, remember that we set a 16 megawatt cap for the grid. So because we're using a 15 sub-hourly meteor data, basically we have divided that 16 into 4. So basically at these different times, the maximum that the grid can allow is basically these 4 megawatt, 4 megawatt, 4 and 4. That when we sum this is going to account for the 16 megawatt hour. All right. So right now, let's go back to the slides, and we're going to do a comparison here. So this is something that we can notice in the layout regarding the DC BESS, the AC coupled BESS. So we can see here that the DC couple, we have the batteries inside our PV plant area. So depending on how much space you will have, right? And if you are already maximizing your plant, or if you still have quite some space, then also depending on the configuration. So for instance, right now we are using the power station on the road, which also has the batteries along with it. But we also have the option to have the power station inside the DC field. And what happens is that we're gonna take one structure out and put the power station there. So in these cases, and let's say that we are already maximizing our PV plant area as much as we can, then if we're gonna go with the DC coupled system, we can see some decrease in the module quantity, right? Because we're gonna be taking some structures out in place of these elements. So it's something to consider whenever you're choosing between one of these options. But let's say that you have space outside of your PV plant area, then you can always have the system installed there. Now, the bill of quantities. So here we could see a huge difference between these two, DC BESS, AC BESS. So it definitely is something that can affect the costs, right? So because here on the AC couple, we have inverters, we have transformers, we have civil works trenches. So a lot of the things that we're seeing here on the AC couple, um, on the DC BESS, these are actually happening on the PV plant bill of quantities, right? A lot of the civil works, trenches. So if we're doing the DC couple, we should see very, very small differences in there, right? Now, if we look on the energy side, so right now we basically have the two tables, one for the DC couple, the other one for the AC couple. Again, so basically here, the power or the losses that our system is going to have due to any excess, if we are oversizing our system, right? We can use the DC couple BESS so that we don't just waste power. But if you know that the grid has a specific cap, and you want to take advantage of that, then using the AC couple is also a good option. So basically, both systems, DC couple BESS and AC couple BESS, both present advantages and disadvantages. Again, regarding like how much area you will have, the let's say the power station configuration, the bill of quantities, which can affect the financial or the capex side, the grid curtailment, whether you have that cap or not, you can make that decision. And maybe let's say like also taking into account the power outages. So AC couple tends to be best used or more used in these particular cases. So right now it's time for some questions. So let's see here the questions. So can pvDesign do standalone BESS? Unfortunately, at the moment, no, but this is a feedback that we have received in the past, and it is something that the team is currently analyzing or studying. Okay. So we also have another question here. What does retrofit means? So retrofit means that we are either upgrading or replacing some equipments in an existential system. So we could be changing things such as modules, inverters, other accessories. And it could also mean that we are adding a BESS system to this existing solar system. What is the meaning of PCS? So PCS means power conversion system. And in this container is where the inverter that is you guys are interested into like into more details for the DC couple, we're gonna do another webinar this quarter. For DC coupling, will you allow string inverters to be built in? At the moment, or at least the configuration that we have right now, the DC coupling is only enabled for central inverters. Does the use case of BESS affect the choice between DC and AC coupled? I would say that for the one that we did here is just to kind of present you with the different options and the ways that you guys can use the configurations and the parameters in the design so that you can make that decision, right? So how much land you're going to have, and all of those different things that we talked about. So it's something that you will need to analyze for your particular system, and then you can choose which one is going to be best. I cannot. So I hear there's someone saying that you cannot hear me. Can you guys hear me? Let's see any other question. So which one is more efficient? So DC couple tends to be more efficient, and the reason is because on the AC couple, we're getting the power. So everything is gonna start on the PV side, which is DC, and then it has an inverter, is gonna go to AC, and then goes through another inverter, and then back to DC for the battery. So, like this conversion DC, AC, DC, it tends to have some losses. So because of that, we could say that DC couple tends to be more efficient because of that, because we're just going from DC directly to AC, and that's it. So let's see if we have any other question. So in which container is the DC-DC converter located at? So the DC-DC converter, and let's just go back to pvDesign really quick here. Let's do DC, and then if I open here the schematic diagram, so at least here we are having the DC-DC converter inside the power station. So let's see if there's any other questions. So we are evaluating a hybrid system which injects the energy from the panels to the grid, and the losses are stored in the batteries. Yeah, correct. To the grid, and the losses are stored in batteries, correct. So basically, what the main point is that we are trying to not waste power, right? So when we have a DC-AC ratio above 1, right, where we have more DC than the AC power, there's gonna be losses there because there's just so much energy that our inverter can convert. In these particular cases, then we can use this DC couple system, right? So a lot of people also try to increase the DC-AC ratio to take into account the degradation of the panels by, let's say, like we have a 1.3 or 1.35. There's going to be, in those early years, there's going to be a lot of wasted power. So if it's something that you would like to take advantage, then the option would be to use the DC coupled BESS, or any other one. Okay, so let me see if there's any other question that I probably missed up here. Okay, I don't see any other question. So thank you so much for joining today's webinar. If you have any additional questions, feel free to go to our webpage so you can get in touch with us. Or like I mentioned before, this webinar is going to be recorded so that you can watch it. You can watch the previous AC coupled webinar, and we're gonna do a deep dive into the DC coupled BESS system in this quarter if it's something that you're interested in. So thank you guys so much for joining, and I'll see you guys in the next time.